Welcome to Spring LIB.
Hi, today we're going to be working on a problem where we have a mass on a spring and then you drop a mass of putty on top of this mass. So basically you're increasing the mass of this spring system while it's moving. The problem refers you to an example in the textbook, example 14.5, which is the same problem. We're just going to do a little more exploring around it. So when we're looking at this problem, we're asked what the mass of the putty is so that the amplitude is halved. So we're saying that we want the amplitude after A2 to be equal to A1 over 2, the original amplitude halved. So the example problem has a nice expression ready for what the amplitude after is going to be. So we can see that A2 is going to be equal to A1 times the square root of the mass of the block divided by the mass of the block plus the mass of the putty, that extra mass. So now we just got to do a little bit of substitution and a little bit of rearranging. So we can say that A1 over 2 equals A1 times square root of mass divided by mass plus mass putty. The A1s are going to cancel out, and we're going to end up with an expression that looks a lot like 1/4 equals the mass divided by the mass plus the mass of the putty. And we're going to end up with the mass of the putty has to be equal to 3 times the mass of the block. So that's the first part. That's part A. If we move on, we can look at part B, where we're asking what percentage of the energy is going to be dissipated to heat. So the way that we look at that is we're going to look at energy conservation. We're going to say that right before and right after the event of the mass of the putty being attached to the mass on the spring, the energies have to be the same. So what we're going to look at right here is that the energy before, E1, is going to be equal to 1/2 times or 1/2 times the spring constant K times the amplitude 1 squared. That's a generic expression for the amount of energy in a spring. But we're going to look at the specific case of when the is also equal to 1/2 mv squared. This is, of course, when the spring is in the middle of its amplitude, where the amplitude is 0, rather. So we're looking at that one particular spot when the mass of putty is dropped onto the mass. From this, we can get an expression, and I'm going to mark this with a V1 for V1. So we can say that V1 is going to be equal to the square root of K over M times A1. And that's just from rearranging this little problem. Cool, and then we need an expression for the energy afterwards. So E2, we're going to say, is going to be equal to 1/2 times the mass plus the mass of the putty times A squared, A2 squared. Not A2 squared, but rather V2 squared. In a similar way, we can get an expression for V2 by saying that this is going to be equal to 1/2 K A2 squared, because that spring constant isn't going to change. So from here we can get V2 is going to be equal to the square root of K divided by M plus MP times A2, which we know A2 is going to be A1 over 2. So we're going to just call that A1 over 2. Simplify things for a little bit for later. So when we're looking at this, we're just going to try and put these back in and then divide the two. We're dividing E2 by E1 to see what the energy loss is before and after. So I'm going to do that over to the left underneath this spring. So we're going to have E2 is going to be equal to 1/2 the mass plus the mass of the putty times square root of K over mass plus mass putty times A1 divided by 2, and that whole quantity is going to be squared. And then we're going to divide that by the expression that we have for E1. A lot of things are going to cancel. The A1 squared is going to cancel for sure, and we're going to have this 1/2 cancel as well. So if we're looking for the expression for E2 divided by E1, we're going to have an equation that is mass plus mass putty divided by just the mass is going to be equal to, and on this side, we're going to have K divided by mass plus mass putty times 1/4 from that A1 over 2. And then down here, we're going to have K divided by mass. The A1s are going to cancel out, as I said before. If you do a little bit of rearranging on this and make the substitution that the mass of the putty is equal to 3m, you get that E2 divided by E1 is going to be equal to 1/4, which means that 1/4 of the energy is still mechanical, is still contained within the spring, which means that 3/4 of the energy has been lost to heat. So that's how you do this problem, considering conservation of energy and just looking at some pretty simple math. I hope this helped you.